humans gained the power to transform this planet to such an extent. Looking at Earth at night shows how successful we have been in exploiting and using energy, as well as its importance to our existence. Energy is very important to everyone. We use it to build structures that surround and protect us. We use it to power transportation and light our homes. More importantly, energy is essential for life itself. Without energy from food, we would die. But what exactly is energy and why is it so useful to us? To answer these questions, scientists created a set of strange rules. It connects everything from engines, humans to stars. It turns out that energy is not only important in daily life, but also helps us understand the entire universe. This film tells the fascinating story of how we discovered the laws that govern the universe. It's the story of how we realized all forms of energy have a fate of degradation and decay, moving from order to chaos. It's the story of how the universe harnesses this amazing process to create everything around us. Throughout history, humans have devised many ways to extract energy from the environment. From picking fruits, burning wood to harnessing water power. But about 300 years ago, something amazing happened. Humans developed machines that processed enormous amounts of energy, performing tasks previously unimaginable. This happened thanks to many people and for various reasons. Let's begin the story with one of the most fascinating figures in scientific history. One of the first people to try to understand energy. Gottfried Leibniz was a diplomat, scientist, philosopher, and genius. He always tried to understand how the universe works. Leibniz and many contemporaries completely believed that the world around them was a giant machine, designed by an all-powerful and wise being. And if you understood how the machine worked, you could also understand the universe and the principles that make it up. Therefore, for Leibniz, there was a close connection between theology and philosophy, with engineering and mechanics. It was this connection between philosophy and engineering that led him in 1676 to study a seemingly very simple question. What happens when objects collide? This was a problem that Leibniz and many contemporaries were struggling with. When two balls collide, motion transfers from one to the other. It seemed like something was being transmitted between them, and this was what Leibniz called living force. He considered it as an entity, a real substance exchanged during collisions. Leibniz believed the world was a living machine, and inside it had a certain amount of living force placed by God during creation, so it would never change. Therefore, the amount of living force in the world was conserved. The question was how to determine it. Leibniz soon found a simple mathematical formula to describe living force. But he would also discover something else. He realized that in gunpowder, fire, and steam, their energy was being released intensely and powerfully. If this could be harnessed, it could give humanity power beyond imagination. Leibniz soon became fascinated with ways to attract energy. As a frequent letter writer, Leibniz had a correspondence relationship with a young French scientist named Denis Pepin. In their letter exchange, Leibniz and Pepin realized that the energy released in certain situations could actually be harnessed. Energy could be transformed into some useful forms of work, but how far this idea could be implemented? Pepin had no doubt. This is an excerpt from his letter to Leibniz. I can assure you that, the further I go, the more reasons I find to appreciate this invention, which theoretically could enhance human power infinitely. But in practice, I believe, I can say without exaggeration, that one person by this means would be able to do as much work as 100 others could do without it. At this point, you might expect that Leibniz and Pepin had changed the world forever. Their ideas were profound and vast, but they hadn't pushed things forward. So something much more concrete was needed. We need innovation, industry, need countless workers and skilled craftsmen to apply these ideas and test them in novel ways. In the century following Linnaeus and Pepin, this happened in the most impressive way imaginable. 150 years later, based on Linnaeus and Pepin's discussions, energy had been spectacularly harnessed. The machines they dreamed of had become reality. Steam engines were now the cutting-edge technology of the 19th century. If we look at the development of civilization, then a major step was the steam engine, because it replaced muscle, including our own, with steam power. And steam power was truly limitless and crucial for achieving things nearly unimaginable. Steam technology would do more than just transform human society. It would uncover the truth about what Linnaeus called energy, and reveal new insights into the workings of our universe. But alongside all the great successes and immense power that engines gave their creators, there was still much confusion and mystery surrounding how and why they worked. Especially questions like, how efficient could they be made? Were there any limits to their power? Ultimately, people wanted to know what could be achieved with steam. The reason these questions persisted was quite simple. Almost no one understood the fundamental nature of the steam engine. Very few knew about the universal principles underlying it. But this great transport machine we consider the early steam engine was actually the seed of understanding everything happening in the universe. It might sound incredible, but steam engines contained within them the secrets of the universe. In March 1814, during Napoleon's War, when Napoleon and his army were fighting elsewhere, Paris itself was suffering continuous attacks from the Allied forces of Russia, Prussia, and Austria, and the city's people were deployed around important positions to defend them. At the Château de Vincennes, which was being defended by a group of inexperienced young students, who were forced to retreat under continuous artillery fire. One of them was a talented young scientist and soldier. His name was Nicolas Leonard Sadi Carnot, and the humiliation he felt drove him to discover insights into how all engines work. Carnot came from a highly respected military family. After France's defeat here and elsewhere across Europe, he was determined to restore French pride. What really bothered Carnot was the technological superiority that France's enemies seemed to possess. And particularly, England had this huge advantage both militarily and economically, thanks to master and steam power. So, Carnot vowed to truly try to understand how steam engines work and use that knowledge for the benefit of France. He stated very clearly that if you could take the steam engine away from England, the British Empire would collapse. And he wrote after the failure of the French army, proposing to literally analyze the source of Britain's power by analyzing how fire and heat engines operate. Living on a modest income with his brother Hippolyte in a small apartment in Paris in 1824, Carnot wrote the now legendary Reflections on the Motive Power of Fire. In just under 60 pages, he developed and summarized the fundamental workings of all heat engines. Thank you for watching the video. Please subscribe to the Unseen Realm channel for more exciting videos. This idea has guided engineers for 200 years. Ultimately, the car engine is more efficient than the steam engine because it runs at much higher temperatures. Jet engines are even more efficient due to the incredible temperatures they can operate at. Carnot revealed that heat engines are not just clever inventions, they tap into a deeper property of nature. They are harnessing the flow of energy between hot and cold. Carnot glimpsed the true nature of heat engines and, in doing so, initiated a new branch of science. But he would never see the impact his ideas would have on the world. In 1832, a cholera epidemic spread throughout Paris, so severe it could wipe out nearly 19,000 people. At that time, science had no real understanding of how the disease spread, so it must have been terrifying. Carnot, undeterred by the risks, decided to study and document the spread of the disease. But unfortunately, he contracted the illness and died a day later. He was only 36 years old. Many of his valuable scientific papers were burned to prevent the spread of the infectious disease. And his ideas temporarily fell into obscurity. It seemed the world was not yet ready for Carnot. Carnot made the first major contribution to thermodynamics. But as the 19th century progressed, research on heat, motion, and energy began to attract a broader scientific community. Soon, it was realized that these ideas could do more than just explain how heat engines work. Just as Linus suspected with his concept of vital force, these ideas could be applied on a much larger scale. By the mid-19th century, scientists and engineers had precisely identified the relationship between different forms of energy. They measured how much of one specific type of energy was needed to produce a certain amount of another. For example, the energy required to heat 30 milliliters of water by 1 degree Celsius equals the energy needed to lift a 12.5 kilograms object by 1 meter. The deeper point people realized here is that although work and heat seem very different, they are actually two sides of the same thing: energy. This idea later became known as the first law of thermodynamics. The first law reveals that energy is never created or lost. It only transforms from one form to another. 19th century scientists realized this meant the total energy of the entire universe is actually fixed. Surprisingly, there is a certain amount of energy that can transform into various forms, so in a steam engine, energy is not created. It only converts from heat to mechanical work. But as impressive as the first law is, it raises a big question. What exactly happens when one form of energy transforms into another? In fact, why does it do that? The answer would partly be found by German scientist Rudolf Clausius. And it would form the basis of the second law of thermodynamics. Rudolf Clausius was an outstanding German physics student from Pomerania, studied in Berlin, and at a ridiculously young age became a very distinguished professor in Berlin, and later in Zurich at the newly established Swiss Federal Institute of Technology. And in the 1850s and 60s, Clausius provided the first truly coherent, comprehensive mathematical analysis of how thermodynamics works. Clausius realized that in the universe, not only is there a fixed amount of energy, but that energy seems to follow a very strict rule. Simply put, energy in the form of heat always moves in a specific direction. His insight is actually one of the most important ideas in all of science. As Clausius said, heat cannot spontaneously transfer from a colder body to a hotter one. This is a very intuitive idea. If left alone, a hot cup of tea will always cool down. This means heat transfers from a hot cup to your hand, and then from your hand to your body. This seems completely natural, but it is a crucial insight. Heat flow is a one-way process, deeply embedded in the functioning of the entire universe. Of course, objects can get hotter, but you always need to do something to them for this to happen. Left alone, energy always seems to go from concentrated. One of the most famous sayings in science is by biochemist Obersendorf. He said that science is seeing what others have seen but thinking what no one has thought. And Clausius looked at the everyday world and saw what everyone had seen. Heat does not naturally transfer from a cold object to a hot one. It always goes in the opposite direction. But he didn't just talk about it. He actually sat down and thought about it. Clausius synthesized all the ideas about energy transfer and placed them in a mathematical context. It can be summarized by this equation: ES ET is greater than or equal to 0. Clausius introduced a new quantity that he called entropy, denoted as S. Essentially, the meaning of this equation is that when heat transfers from a hotter object to a colder one, entropy always increases. Entropy seems to be a measure of the dissipation or spreading out of heat. When hot objects cool down, their entropy increases. Clausius noticed that in any isolated system, this process is irreversible. Clausius was very confident in his mathematical abilities. He realized that this irreversible process is occurring in the larger universe. He deduced that the entropy of the entire universe must increase to a maximum, and we cannot avoid this. This idea is called the second law of thermodynamics, and it turns out to be stranger, more beautiful, and more universal than anything Clausius could have imagined. The second law of thermodynamics seems to say that all heat-emitting objects are connected in some way. All heat-emitting objects are part of an irreversible process happening everywhere. A widespread and dispersing process, an entropy-increasing process. It seems the universe shares the same fate as a cup of tea. The remarkable thing about Victorian scientists is that they could make these leaps. And they could see that their research on thermometers in glass tubes could actually be extrapolated. Could be expanded to encompass the entire universe. Despite the successes of thermodynamics in the mid-19th century, there were great debates and confusion on the topic. What is this so-called entropy, and why does it always increase? Answering this question would require an astonishing intellectual leap, but it would ultimately reveal the truth about energy as well as the many forms of order and chaos we see in the universe around us. Many scientists would tackle the mysterious concept of entropy, but one more than any other would illuminate the truth. He would point out what entropy really is and why over time it always increases. His name was Ludwig Boltzmann, and he was one of the true revolutionaries of science. Boltzmann was born in Vienna in 1844. It was a world of scientific and cultural certainty. But Boltzmann paid little attention to the ingrained beliefs of his contemporaries. For him, the material world was something best explored with an open mind. In fact, Boltzmann was not a stereotypical scientist. He had the kind of temperament that most people might associate with great artists. He was brutally logical and analytical. But while working, he would experience terrible crises and mental breakdowns, in which Boltzmann truly thought the world was cracking. However, these also came with some of the deepest insights into the nature of our world. Beyond mathematics, Boltzmann was passionate about music and fascinated by Wagner's grand, dramatic operas, as well as the raw emotion of Beethoven. He was an excellent pianist and could immerse himself for hours in the works of his favorite composers, just as he could immerse himself in profound mathematical theories. Boltzmann was a scientist guided by emotion and instinct, as well as a belief in the power of mathematics to decode nature's secrets. It was this trait that made him one of the champions of a new, shocking, and controversial theory. A theory that could describe reality at a very small scale, much smaller than anything we can see with the naked eye. In the latter half of the 19th century, a small group of scientists began to speculate that, at the smallest scale, the universe might operate very differently from our everyday experience. If you could look closely enough, it seemed the universe might be made up of tiny, hard particles in constant motion. Viewed from an atomic perspective, heat would suddenly become a much less mysterious concept. Boltzmann and others saw that if a part is hot, it simply means its atoms are moving faster. Viewing the world as atoms seemed an incredibly powerful idea, but this picture of the universe had one seemingly unsolvable problem. How could one study trillions upon trillions of atoms, even in a very small volume of gas? How can we formulate mathematical equations to describe all of this? After all, atoms continuously collide with each other, change direction, alter speed, and the number of atoms is so vast that it seems like an unsolvable problem. But then Pullman realized there was a way. Pullman saw more clearly than anyone that for physics to analyze this new reality, it had to abandon certainty. Instead of trying to understand and measure the exact motion of each individual atom, Pullman showed it was possible to build workable theories using only probabilities. That atoms would move at certain speeds and in certain directions. Pullman had moved himself inside matter. He imagined a world beneath our everyday reality and found a mathematical way to describe it. At this scale, one day Pullman would find a way to decode the deepest secret of energy, despite widespread opposition to his theories. Pullman's ideas were controversial, and you must remember that today we take atoms for granted. But the reason we take atoms for granted is precisely because Pullman's mathematics matched experiments so well. One of the most surprising aspects of this story is that many of Pullman's contemporaries viewed his ideas about atoms with intense hostility. Today, the existence of atoms, the idea that all matter is composed of tiny particles, is something we accept without question. As time, there were eminent physicists, notably, who didn't. Because no one had ever seen an atom, and perhaps never would, how could these particles be considered real? After one of Paumann's lectures on atomic theory in Vienna, the great Austrian physicist, Enigma, stood up and spoke simply. "I don't believe atoms exist." It was both sharp and dismissive. And if such a remark came from a highly regarded scientist like Enigma, then it would hurt twice as much. They argue that no, atoms don't exist. They're just names, labels, convenient fictions, computational devices. T really exist. We can. And for that reason, as Paumann's critics said, he was a fantasist. But Paumann was right. He looked deeper into reality than anyone else had dared, and saw that the universe can be built from the atomic hypothesis, and understood through clear mathematics. The foundation and certainty of 19th century science were beginning to crumble. As Paumann stared into his brave new atomic world, he began to realize his new vision of the universe. Contained within it the explanation for one of science's greatest mysteries. Paumann saw that atoms could reveal why the second law of thermodynamics is true. Why nature engages in an irreversible process. Atoms have the ability to reveal what entropy really is, and why it must always increase. Paumann understood that everything is made up of much smaller components. Fundamentally, everything we see is a collection of trillions of atoms and molecules. And this is the key to his insight into entropy and the second law. Paumann saw what Clausius could not. The real reason why a hot object let alone will always cool down. Imagine a hot metal block. The atoms inside it are vibrating around, but as they vibrate, the atoms at the edge of the object transfer some of their energy to the atoms on the table's surface. These atoms then collide with their neighboring atoms. And in this way, thermal energy spreads out and distributes slowly and very naturally. The system has transitioned from a state of very special order, with all energy concentrated in one place, to a state of chaos, where the same energy is now distributed among more atoms. Paumann's brilliant mind realized this entire process can be described mathematically. Paumann's great contribution was that he was able to derive a formula that allows you to calculate the chaos of a system. This is Paumann's famous equation. S equals Carlock, unit is quad. It would be his lasting contribution to science. So much so that it was engraved on his tombstone in Bonn. In essence, this equation means there are more ways for things to be messy and disordered than for them to be neat and orderly. That's why if left alone, the universe will always become more chaotic. Everything moves from order to chaos. That's the law that applies to everything. From a falling vase to a burning star, a hot cup of tea to the products we consume daily. All of these demonstrate the universe's tendency to move from order to chaos. Chaos is the fate of everything. Clausius showed that what he called entropy is always increasing. Now, Paumann revealed what this really means. Entropy is actually a measure of the degree of chaos in all things. Energy is collapsing as we speak. So the second law talks about the increase in entropy. This is just a technical way of saying that everything is getting worse. Paumann's passionate and romantic sensitivity, along with his belief in the power of mathematics, led him to one of the most important discoveries in the history of science. But those strong emotions also had a dark side and ultimately were self-destructive. Throughout his life, Paumann was prone to severe depression. Sometimes these were triggered by criticism of his theories, and sometimes they just happened. In 1906, he was forced to take a leave from the institute during a particularly bad period. In September 1906, Paumann and his family were on vacation in Duno, near Twister in Italy. While his wife and family were out at the beach, Paumann hanged himself, abruptly ending his brief time in our universe. But perhaps the saddest scene in Paumann's story is that just a few years after his death, the ideas that had been attacked and ridiculed throughout his life were finally accepted. Moreover, they had become the new orthodox science. There is ultimately no escape from entropy. It is this ultimate shift from order to decay and chaos that dominates all of us. Hammond's equation contains within it the death of everything. From a porcelain vase to human life to the universe itself. The process of transformation and degradation is inevitable. The second law states that the universe itself must one day reach the point of maximum entropy. Maximum disorder, the universe itself must one day die. If everything tends toward chaos, if everything becomes chaos, you might wonder how we exist at all. How exactly did the universe manage to create the complexity and delicate structure of life on Earth? Contrary to what you might think, it is thanks to the second law that all of this exists. The great disorder of the universe gives rise to its complexity. It is possible to harness this natural flow from order to disorder. To exploit the process and create something new, to create new order, new structure. That is what the early steam pioneers inadvertently encountered with their engines. And that is what powers everything we consider special in our world. From cars to buildings, to works of art, even life itself. The car engine, like all other engines, is designed to harness the second law. It starts with something good and orderly, like this gasoline, full of energy. But when burned in the engine, it turns this liquid into a gaseous mixture with a volume over 2,000 times larger. Not to mention releasing heat and sound into the environment, it is turning order into disorder. What's particularly clever about the car is that it can harness the dissipating energy. It can capture a small portion of that energy and use it for a more orderly process. Like making the pistons turn the wheels, that's what engines do. They harness the flow from order to chaos and do something useful. But it's not just cars. Evolution has designed our bodies to operate on the same principle. If you eat this chocolate bar full of good, orderly energy, your body processes it and turns it into more chaotic energy, but consumes the energy gained itself. Both cars and humans power themselves by harnessing the great cosmic flow from order to chaos. Although overall, the world is breaking down into chaos, it's happening in an extremely interesting way. It's like a waterfall pouring down, but the waterfall sprays out a spray of structure, and that spray could be you or me, or a golden daffodil or anything. So you can see that the expansion of the universe, this collapse into chaos, can actually be constructive. Steam engines, power plants, life on Earth, all of these harness the cosmic flow from order to chaos. They learned to harness the universe. But as humanity evolves, we must find new concentrated energy sources that we can break down. To drive the process of building our technology, cities, and society requires more than ever before. From food, wood to fossil fuels, throughout human history, we have discovered increasingly concentrated forms of energy to harness and develop. Now in the 21st century, we are on the verge of harnessing the ultimate concentrated energy form, what powers the sun, Hero. This is the Codium Fusion Energy Center in Oxford, where they're trying to recreate a star on Earth. As you can imagine, creating and containing a small star is not easy, requiring hundreds of people and extremely sophisticated technologies. This machine is called a tokamak, designed to extract the highly concentrated ancient form of energy, the ordered energy of hydrogen atoms. These tiny energy packets were formed from the Circular universe just 3 minutes after the moment of birth. By using the tokamak, we can extract the concentrated energy in these atoms through their fusion. Inside the tokamak machine, 2 types of hydrogen gas, deuterium and tritium, are mixed, forming a superheated state called plasma. When operating, this plasma can reach an astonishing temperature of 150 million degrees. Large magnets on the tokamak walls contain the plasma and prevent it from touching the edges, where it can cool down. When hot enough, the 2 types of hydrogen atoms fuse together, forming helium and releasing neutrons. These neutrons fly out of the plasma and hit the walls of the tokamak. But they carry energy, and hopefully one day this energy can be used to heat water, turning it into steam, running turbines and generating electricity. Essentially, for a brief moment inside the tokamak, a small donut-shaped star is created.
The problem is that it's extremely difficult to maintain a fusion reaction long enough to recover energy from it.
And that's what scientists at COHAM are striving to perfect. It's a kind of boundary between physics and engineering. How do we keep this very hot thing, which is plasma? And how to optimize the method of keeping it there,
improving the performance of the plasma.
So what we really want is
For the particles to stay in there as long as possible, to maximize the chance of colliding with each other.
Scientists are trying to push this to the limit with what they have in this machine. And anything they learn to better understand plasma will also help design a better machine in the future.
What the tokamak is doing is harnessing the fertile remnants of the Big Bang, extracting concentrated energy obtained from the beginning of time. Since hydrogen is the most abundant element in the universe, if future machines can sustain fusion reactions,
they will give us the ability to provide nearly limitless energy.
From a science that began as a byproduct of questions about steam engines, thermodynamics has had an incredible impact on our entire lives.
It has shown us why we must consume concentrated energy to survive and revealed how the universe might end. Looking at Earth at night shows how a seemingly simple idea has transformed this planet.
Over the past 300 years, we have developed more ingenious methods than ever before
to extract concentrated energy sources from the world around us. But all our efforts and achievements are quite meaningless when viewed from the broader cosmic perspective. From that viewpoint, all we are doing is trying to maintain this small order in a disintegrating universe. Although we can never escape our ultimate fate, the laws of physics have allowed us to have this creative, beautiful, brief moment in the process of the great cosmic release.
Hopefully, by understanding the universe in more detail than ever before,
we can extend this moment for many millions, even billions of years to come.